What's up, PreCalc? Here we are with 8.3. Inverse square of a matrix. This section further develops the algebra of matrices. To begin, consider the real number equation a times x equals b. To solve this equation for x, you would multiply both sides of the equation by a inverse, or divide by a, in order to solve for x. A inverse is the multiplicative inverse, because a inverse times a equals 1. So matrices are going to have a similar property here. We're going to try to find the inverse matrix that we can multiply to another matrix and have it equal the identity matrix, which is that diagonal row of 1s going from top left to bottom right with all other zeros. Alright, show that B is the inverse of A. To show that two matrices are inverses of each other, it has to work both ways, A times B and then B times A. Both have to result in the inverse matrix. So if we go A times B, we have negative 1, 2, negative 1, 1, times 1, negative 2, 1, negative 1. Alright, we'll do the work matrix for the first one, and then the second one we'll just kind of go with it. Alright, so rows times columns. So we got negative 1 times 1 is negative 1. And 2 times 1 is 2. Negative 1 times negative 2 is going to be positive 2. 2 times negative 1, we have plus a negative 2 there. Okay, bottom row, first column here, we got negative 1 times 1 and 1 times 1. Negative 1 times negative 2 is going to be positive 2. 1 times negative 1. So taking a look there, we have 1, 0, 0, 1. We got our diagonal row of 1s with zeros everywhere else. Let's see if it works the other way. So with B in front, 1, negative 2, 1, negative 1, negative 1, 2, negative 1, 1. Okay, we'll have 1 times negative 1 for negative 1, negative 2 times negative 1 for positive 2, negative 1, positive 2, 1. 1 times 2 is 2, negative 2 times 1 is negative 2, that'll be a 0. 1 times negative 1 is negative 1, negative 1 times negative 1 is positive 1, those would add to 0. 2 and a negative 1 is 1. So it works both ways, so they are inverses. So A times B equals the identity matrix. Same thing as B times A, so they are inverses. A and B are inverse matrices. Alright, if matrix A has an inverse, it's called invertible or non-singular. Otherwise, if it doesn't have an inverse, it's called singular. A non-square matrix cannot have an inverse. To see this, note that if A is of order mn and B is order of nm, where m and n are not the same, they're different orders, the products would be different sizes. Right? So if I had a 2 by 3 times a 3 by 2 or whatever, it's not going to always work out. Okay? Not all square matrices have inverses either. However, if a matrix does have an inverse, that inverse will be unique. Let A be a square matrix of order n Write the n by 2n matrix that consists of the given matrix A on the left and the identity matrix on the right. So let's say we had one of our original ones up here, like 1, -2, 1, -1. We'll have that over here. Then we'll have our identity matrix 1, 0, 0, 1 over here. Okay, so that's what you can kind of visualize now. If possible, reduce the first one to the identity matrix using row operations on the entire thing. Okay, and then when you're changing what the identity matrix is on the right, whatever that is at the end, it's going to be your inverse. Okay, so you're starting off with your original matrix, and then your inverse matrix on the right, 1, 0, 0, 1. You're doing your row operations in order to make A be 1, 0, 0, 1. And whatever those row operations do and change this one, what this one ends up being is your inverse. It's kind of crazy, but it works. Let's take a look. Okay, so we have 1, 4, -1, -3. Okay, and I do the bar, you can do the dots, and we want 1, 0, 0, 1. So we're focusing on changing this side to be that, and then whatever the row operations do to this side, whatever it ends up being at the end, when this one gets to be the inverse, whatever's left over here would be the actual inverse to what we started with. Okay, so step 1, I want a 1 in that top left corner. Good, it's already there. Step 2, I want a 0 there. So we need to do row 1 plus row 2. So we have 1, 4, 1, 0. Okay, now row 1 plus row 2, that's going to make that be 0. And that's going to make, oh, look at that, that's going to make that be a 1. But now we have to do this over here. 1 plus 0 is 1, and 0 plus 1 is 1. See how this side's changing with it? Okay, so now we have a 1 there, a 0, and this spot's a 1. So now we're going to build it back up. We need this spot to be a 0. We need minus 4R2 plus R1. So that's going to be a 1. -4 plus 4 is 0. -4 plus 1 is going to be -3. -4 plus 0 is -4. 0, 1, 1, 1. So the inverse matrix to that is going to be -3, -4, 1, 1. Okay, so you had your original matrix on the left. We put the inverse, or we put the identity matrix on the right. 1, 0, 0, 1. Regular matrix, identity matrix. Okay, now we do the row operations to change this one into the identity matrix, and whatever happens to this side, that is what our inverse is to A. Okay, all right, now let's take it up a notch. And now that you know what's kind of going on, let's see if you can push pause and try to make it work for this one. I know it's a 3x3. It's a little bit bigger. I'm looking at 1, 2, 3, so like 6 matrices. You're starting out one, and then 5 moves, I guess you would call it, to get it done. Let's push pause and give it a try. All right, welcome back. Let's see how we did. Okay. So we have our original matrix. We have the identity matrix over here. Okay, we're starting off with a leading one. That's what I want. So next we need to focus on getting zeros below it. Okay, we already have a 0 in row 3. I need a 0 in row 2. So I'm going to go -3 times R1 and add it to R2. So that's going to give me a 0 there, 2, 1. That's also going to change this line. Negative 3 plus 0 is negative 3. 0 plus 1, 0 plus 0. So I have 1 with all zeros. Okay. Next, I want that to be a 1. All right. Tempting to kind of just divide it all by 2, but then we're going to have a lot of fractions. Not really feeling that. Let's do row 3 plus row 2, and that'll make that be a 1. So if I do row 3 plus row 2, 2 and a negative 1 is going to be that 1. 0 and 1 still that 1. Negative 3, 1. And then we'll pick up this 1 for the last spot there. 1 with all zeros. We got a 1. Now we need this to be a 0. So now we're going to come right back and do row 2 plus row 3. Okay, and that's going to give me 0, 0, 1. And now we have negative 3, 1, 2 on this side. 1 with all zeros. We have a 1 with a 0. We even have a 1 already here. So now it's time to go back up. We want these to be zeros. Okay, we could probably combine. You could probably combine these two together and do negative. This was a tricky one. So I would have probably have gone negative row 3 to row 2 and row 1. But look at this. If you do negative row 2 to row 1 right away, you can get rid of both of those. So that if you saw that, you could do that way. I probably would have just done negative row 3 to row 2 and row 1. And then I would have came back and then got that one. But we could do negative row 2 and got rid of both of those, and then come back and do the negative row 3 to row 2 there. Either way would work. Either way would work. And we finish with, we got our diagonal 1s here with all zeros. And our inverse matrix, we got 4, negative 1, negative 1, 0, 0, negative 1, negative 3, 1, 2. There it is in all its splendor. Take a look. Okay. So the augmented matrix with the identity matrix on the right-hand side, this process works out pretty good for 3x3s. Okay, a 2x2 wasn't too bad either, but there's actually what some would probably consider to be a quicker way. We probably looked at this a little bit in Algebra 2a with the formula. So we're going to look at this again. Using Gauss-Jordan elimination to find the inverse of a matrix works well, even as a computer technique, for matrices of 3x3 or greater. For 2x2 matrices, however, many people prefer the formula for the inverse rather than the Gauss-Jordan. So if matrix A equals A, B, C, D, A inverse would be 1 over AD minus BC, subtract the diagonals, AD minus BC, and then we're going to flip-flop A and D, and we change the signs on C and B. I probably have like 5 more minutes. All right. So, following this formula, we have 1 over AD minus BC. We flip-flop these two. A and D flip-flop. B and C change their signs. All right, so let's see what we can do. So A inverse equals, we have 1 over those two diagonals there, A times D, so we have 6 minus B times C, negative 1 times negative 2. So we have 6 minus, well, actually negative makes that a plus, so it is 6 minus 2, so we have 1/4 getting multiplied. 2, we're going to flip-flop these two again. Okay, we flip-flop A and D, those switch spots, so 2 and 3 trade spots. And these two just change their signs. They stay where they're at, but they change their sign, so positive 1, positive 2. And then we bring that 1, well, I guess the answer key here left the 1/4 out in front. You can also bring it in if you're not allergic to fractions. So 2 times 1/4 would be 1/2, 1/4, 1/2, and 3/4. Okay? Let's see what happens on this other one. B inverse. 1 over 3 times 2 is 6. Minus negative times negative is going to be 6 again. Oh, 1 over 0. We can't divide by 0. So this is not invertible. No inverse. No inverse there because we got 0 in the denominator. Can't do it. Alright, you know that a system of linear equations can have exactly one solution, infinitely many solutions, or no solution. If the coefficient matrix A of a square system is invertible, the system will have a unique solution, which is defined as follows. If A is an invertible matrix, the system of a linear equations represented by AX equals B will have a unique solution given by A inverse times B, which is how we kind of did things with the 3x3s in Algebra 2. Okay, we typed them into the calculator, into matrix A, and then we typed the answer side into matrix B, and we did A inverse times B. Alright. So, let's use an inverse matrix to solve the system of linear equations. It's a 2 by 2, so I'm probably just going to use the formula. Alright, and no, we're not just going to type this into the calculator. You're going to have to either use the augmented matrix strategy to come up with the inverse, or the formula here. If it's a 2 by 2, we could use that to come up with the inverse. So we have matrix A, which is 3, 4, 5, 3. Times xy, and that's going to equal our matrix B of negative 2, 4. Alright, so we need to find our A inverse. So A inverse, we have 1 over, multiply the diagonals, 3 times 3 is 9, minus 4 times 5 is 20. We're going to have negative 1/11. Negative 1/11 times, we flip-flop those, so 3 and 3 flip-flop, so you really can't even tell. And then 4 and 5 change their sign. Okay. It might be a little, let's see. So you can leave this constant out and then do your inverse part times b and then take the constant multiplier on the outside times it, or you can push it through. I would probably, if I was doing this, I would probably push it through, because to me this doesn't seem like it's the inverse quite yet, so I would probably have it in there, negative 3/11, positive now 4/11, positive 5/11, negative 3/11. Okay? So x equals A inverse times B. Okay, rows times columns. We got positive 6/11 plus 16/11. And then rows times columns. Row times column. We got 20/11. And, nope, I lied. Negative 10/11. And then negative 12/11. So we got 22/11, negative 22/11 for our answer of 2, negative 2. So x equals 2, y equals negative 2. All right. Sorry that went so vertical. All right, folks, there you go. We will look at this a little bit more tomorrow and talk about what's on your quiz, and then we'll have some fun with the quiz. All right, thanks for watching. Best of luck.